Okay, good morning, everyone. We're starting the session in a moment. Can you just confirm if there's anyone presenting here in the room? Anyone online who's going to present? Okay, so apparently not, which means that we're missing our first speaker. Just let me check if I can find him because he was going to be here. Hello?
Foi o meu computador. Estava aqui a aceder também ao online.
Okay, so the first speaker hasn't made it yet, so we will try the second one. So the paper misbehavior detection in OneX using tree-based machine learning techniques. Is anyone here to present this paper? No. Okay, we're lucky enough to have our first speaker. And so we're moving to the third presentation by your name?
Diego Dias.
Okay, muy bien. Very well.
Which one do you want?
No, it's
The other one?
Ali. Yes, this one. Can you finish the problem?
Okay, so Diego Diaz is getting ready, so we're going to have his presentation in just a moment.
Yes, that's it.
So let's give Diego just a bit more time. He's getting ready.
Are you seeing the slides?
Yes, we are.
As soon as you take it online, they are also seeing. Yeah.
Okay, so we're good to go. So I'm handing the floor now to Diego Diaz for his presentation. Please. Okay. Thank you very much, Diego. So we have time for questions. Anyone who'd like to make any question to Diego or anyone online? Okay. So I'll make one question then. I was just trying to understand a bit more about the purpose of this data. So is it like to understand the evolution that people have after they have a stroke, for example? So you can sort of assess if the degree of recovery that they are having when they're recovering from a stroke. Is that the purpose?
I'm a from computer science, but I'm part of a group of neuromotor rehabilitation, physiotherapists and everything. And we need data to train the models to do what you said, and we don't have that much of patients. So we need to do this kind of approach, try to create synthetic data to train the models.
But
that is the purpose. It's to predict the treatment, what kind of treatment the patient needs, how many sessions they're going to need to improve, to get better after post-stroke. That's the purpose.
Okay, but then the purpose of the synthetic data is to extend the available data.
Yeah,
but
same thing.
Yeah, but so why do you need this? Why? I mean, it seems like relatively simple movements. You squat and stuff that you were mentioning. So why does this additional data? What does this additional data brings to the training?
That's only one example, but we have a lot of other movements for upper body also. And to train some deep learning, the deep learning approach, the amount of data we have now is not enough. We couldn't train. Now, doing a fine tuning with LLM, it's doing great with no more synthetic data. But for LSTM, GRU, and others approach, we need more data.
Okay. Okay. Thank you very much. No more questions? No. Okay. You're done. Thank you very much. So I'm just going to check if we have our first speaker, Elio.
Yeah, I am here, Darwish.
Say that again?
Darwish. My name is Darwish Ibrahimi, the next presenter.
No, I was asking for the first one, actually, because the first one was not here, so I was just trying to... But you're the second one?
Yes.
Okay, so apparently we do not have our first speaker, so it's your turn now.
Okay.
So welcome to the floor. And so we're moving to the next presentation, misbehavior detection in VANETs using tree-based machine learning techniques. We'll just give a moment to switch presentations.
Yes. Just in case if there is any problem with this.
Okay, it looks like we're ready, so you're good to go.
Okay, thank you so much, Chair, for so much.
Thank you very much. So now we have time for questions. Yes, please.
Thank you for presentation. You didn't give the details, but just as a quick explanation, what is exactly the input and the output? You just use PDR, SNR, and say it's dominated traffic, or did you use some kind of flow of this PDR and SNR to classify it?
Yeah, actually, in the data set that we use, for sure we have some information regarding the right communication or messages and benign ones. So we train our models based on that. So what do we have there to help us to check whether there is a misbehavior messages or there is an attack or not? We had for example, we have the signal strength and also the packet delivery quality and the other things that I don't recall it for now. Let me see whether I have it on this slide or not. Yes, we have some examples. For example, we have the signal to noise ratio. We check that one, packet delivery ratio, and receive signal strengths and other things that we.
Just from reading of the SSI, PDR, you were able to say this SSI is this record with all this feature, all this 15 feature. You were able to say it's attack or it's not attack, or you must read several records to say now I'm having an attack or not.
No need to check several. Just if we receive a message, for example, this is in case of spoofing. If the signal strength, the received signal strength is different than what we received earlier, then we can know that there is an attacker. It's not the legitimate vehicle who's sending, or maybe the roadside unit. This is one of the things that we consider. But regarding the other type of attacks, other than the spoofing, we talked about jamming attack. So here, when we have a jamming, it means that we have some sort of interference. So we have to check which node is making the interference here in order to avoid receiving any messages that from that vehicle, from the attacker.
Okay, any more questions? Okay, so thank you very much. And we're moving now to, let me check again if our first speaker is now in the room. No. So we have Stephen Leon, okay, our next presenter. We'll just wait for a moment while Steve is going to the stage.
Ok, sim, do câmera agora. Okay, just make sure everyone is on the same page. We are now moving to our fourth presenter, Stephen Leon.
on
on
Bayesian
Bayesian
analysis
analysis
for
for
wildfire
wildfire
classification
classification
in the
in the
United
United
States
States
and
and
Australia
Australia
through
through
spatial
spatial
hierarchical
hierarchical
models.
models.
You just
Just
confirm
confirm
the
on
mic
mic
while
while
still
still
getting
getting
ready
ready
for the
for the
presentation.
presentation.
Yeah, so it's in PDF format, I could send it all out there.
Okay,
Okay,
so
we
go.
go.
So
So
whenever you're ready.
Yeah, so my name is Stephen Leon. I am a Master's of Statistics student at the University of Michigan, Ann Arbor. And yeah, I'll be presenting on Bayesian analysis for wildfire classification in the United States and Australia through spatial hierarchical models. So we're going for classification and then doing some inference just based off of our probabilities. So yeah, a small history of wildfire analysis is what we'll kind of go over. We use the BRMS library, Bayesian regression models using STAN to model some of the different probability distributions. Then we'll be looking at a couple other questions, right? Like, do wildfire climate relationships transfer across continents? We'll be looking at the inference and the interpretability of these models, how effective they are. We'll be talking a little bit about their internals through methodology. In total, we present three, spatial hierarchical, brightness sensitive spatial hierarchical, and mixed effects hierarchical models. So they all kind of represent geolocation in different ways. One uses a spatial kernel. The other, we recycle it for the brightness sensitive one, and then we just use city and state through a hierarchy in our mixed effects hierarchical model. And yeah, our goal is to be able to compare all three and evaluate each and every one of them through the Bayesian lens, right, where we define our posterior in terms of the likelihood and prior, or rather what our probability distribution looks like after adding our data in as a posterior is defined. And yeah, we look at the meaningful insights we can get from that. So yeah, the small history, right? Wildfires date back 440 million years ago to the Silurian era. We've had real early work, right, studying fire growth rates in the 1940s, generalized additive models. There was a paper in 2013 that was pretty successful. So then after that, right, we're into your general AI machine learning era. So up to 2024, right? You see a couple of different classical machine learning methods, random forests, SVMs, KNN logistic regression, Bayesian logistic regression, benchmarking some different accuracies. So most recently in the 2020s, having like the whole image with like pixels of the fires, right, gets us as high as 98.6% accuracy. There were also some works, right, in 2024 using hand-derived features again, just using deep learning neural network, a feed-forward one. That's given us like 89-90% accuracy. 89.6, I think, was the highest architecture in that paper. And then in Australia specifically, right, based on logistic regression, reached 96% accuracy using spatial, temporal, environmental, and meteorological data and those features. Yeah. So we built our own data set based off of NASA's firms. It's like a fire management resource site. 153,916 different fires in the United States and 156,000 fires in Australia are the ones we analyze. Our data, right? We get NDVI from Google Earth Engine, brightness from NASA, soil moisture from Google Earth, then a couple of different meteorological features from Open Meteor API, right? Just your daily kind of statistics, population, daylight, geolocation, city and state. Yeah, so we built our own data set. These features were pretty similar to what was used in the 2024 paper on wildfire classification using feed-forward neural networks. they also used soil moisture and NDVI. NDVI was found in the Australia Bayesian paper to be one of the most impactful features, but we'll get there in a second. So yeah, NDVI and soil moisture were both found to be pretty important. They're sort of our key indicators. The last time we had a paper out from Australia doing wildfire classification, we did not have soil moisture in that model. It turns out to be very important in Australia, more so than the United States. It contributes more to the probability that it's a wildfire or not in our posterior. But yeah, NDVI, right? It's basically just a metric that we get from Google Earth images of vegetation data, and then soil moisture we also get as a metric from Google Earth Engine. Yeah, then how we build our data set is just based off of the complement law as used as early as the 1600s, but I think written down at some point by Kolmogorov in 1933. But yeah, we define the set that doesn't have any wildfires, right, as basically points in Australia or the United States that doesn't fall into our subset of that space that what is it, that has the fires that we downloaded from NASA. So in total, our data set is 1,000 points in each one, 1,000 points of fires, and then 1,000 points that aren't fires. Yeah, and our data set comes out to be pretty proportional. Yes, so we look at just wildfires in general, right? This is our subset, and then this is like our initial fires data set. We can see that we have the same spikes, so we can generally rely on some of the same properties. We see that the timestamp, for example, will have the same distribution for fires, both inside our sample and out. Yeah, and then last little image of the data set. Right, we look at our distribution of the fires just in Australia. Right, a lot of no fires in the center, even though it's the hottest region in the United States. A little bit more spread throughout, not too many trends, but yeah, we see a lot of fires on the coastal regions. Those are ironically issued or points where we had very high AQI, but we ended up not using air quality in these models because it had very little effect. All right, so down into methodology, we use Bayesian regression models using STAN. It is the BRMS library in R. We essentially define it as the posterior, or rather the probability of a wildfire given our predictors. So how we represent it, right, is an inverse logic function, similar to any typical general or linearized model. Where we have our predictors and our coefficients, and our inverse logic function will put our final value or our probability between 0 and 1. So very large positive coefficients for, say, soil moisture would contribute more to our probability. So that's how we tackled interpretability of the model. We look at the coefficients, whether they're positive or negative. So under the hood, right, we're still using the BRMS library, but it runs off of Hamiltonian Monte Carlo to give us these coefficients. And then specifically the library we use uses an implementation based off Gilman and Hoffman's No U-Turn Sampler 2012 paper. This is the algorithm. So that will give us our coefficients. So yeah, we have 3 different models: spatial hierarchical, brightness sensitive, and then mixed effects. So our spatial hierarchical model does pretty well all around. Yeah, 88.58% accuracy in the United States, 86.69 in Australia. We look at area under the curve using true positive and false positive. We come close to 100 around them all. But in the spatial hierarchical model, how we represent geolocation is through a spline with k different knots. And that will use geolocation. It ends up being just a feature in the library, so no additional coding. But yeah, under the hood, it runs as a spline. Yes, so both in the United States and Australia, we come pretty close to just having like a full-on rectangle with two different metrics on a Pareto front, false positive rate and true positive rate. Basically, what we do is once we define the posterior for all of our data instances, right, the probability of a wildfire given all of our different models, we come up with a different threshold, right? And we look at the probability threshold for which we would take it as a wildfire and take it not as a wildfire. And we look at the most optimal true positive rates and false positive rates we can get by moving that threshold up and down. Nothing different than in a typical Pareto front. But yes, then when we take all of our training instances and put them back on a map, they tend to look pretty much identical to what we had earlier with our spatial hierarchical model. Yeah, so now we get a look at our coefficients, and we do see that a lot of the relationships, right, that determine a wildfire do cross over continent. NDVI has been previously observed in other papers to be effective at pinpointing whether or not it's a wildfire. We see the same in this one, right? 1.24 versus 1.47. Precipitation, sort of cloud cover. Soil moisture, we noticed, right, is a big negative contributor to the probability of a wildfire. So it predicts that it's not a wildfire pretty well. Very much so in Australia. Much more so, actually. We have a much greater negative contribution, negative 6.58 versus negative 1.90. But overall, the relationships are very much able to be transferred across continent between the United States and Australia. So some good trends on that. Yeah, this is just what we were talking about. We can see with the coefficients, the probability of a wildfire given a temperature. That, right, goes up as the temperature increases. Whereas as we were talking about, right, in Australia, we see a much bigger contribution in the negative direction for soil moisture in Australia than the United States, but both are negative in general. Yeah, we also make a little bit of modification in a custom Python version. So this becomes the brightness sensitive spatial hierarchical model, where it's the same, but whenever we update our coefficients, we sort of redefine the error to weight it based off of, well, first off, is it a wildfire or not? And if it is, we'll use NASA's brightness data to see just how bright this wildfire is compared to our max one. This is more or less just for inferential purposes, but it'll pull the coefficients in the direction of the steepest descent for our brightest wildfires when we're running Hamiltonian Monte Carlo. So, it still does end up being pretty effective, right? We get 84% accuracy in the United States, 77 in Australia, and a slew of other different metrics. But our biggest point is that we do some polling on the coefficients. NDVI stays like the same in Australia. Soil moisture, we see some issues, but the temperature, right, we end up moving it up in the United States, where we see more success in this modification. In Australia, we have some distractors, such as the hottest region, right, is in the center, where there aren't really any wildfires. So not the best change perhaps for Australia, but in the United States, we get some cool inference where we don't have that issue. We can see for the temperature coefficient. For the brightness sensitive model, we get a 95% credible interval of between 0.1545 and 0.1652, whereas a regular spatial hierarchical model is in between 0.11 and 0.15. So this shortage just shows that temperature has more contribution to predicting our brighter wildfires in a batch, supported by our 95% credible intervals. And that comes to reflect Stephen Boltzmann law, where the luminosity of a fire, right, is proportional to a temperature. So interesting inference that we can do based off of this change to pull our coefficients toward this particular group. And there are some misclassifications that we do fix. For example, in a particular region, say, where this might be of interest, we're able to fix a classification in Hawaii with this model that we actually missed in the United States. But overall, that's very particular to a certain use case. But we do see some examples that's presented in the paper. And our final model is just another mixed effects hierarchical model. This is just a model that we handle a bit differently. It's still implemented in the Bayesian models and STAN library, the BRMS library. But basically for, say, each predictor, soil moisture, for example, we could have a specific one for each different city, creating a hierarchy. So our soil moisture coefficient is going to be different in a different city. So in Sydney and Queensland, we'll end up having two different coefficients. So these models are a lot more customizable. And then we drop the spatial kernel in these models. So we just represent geolocation through the city and the state intercepts. So we end up calling this the mixed effects hierarchical model because we have mixed effects added to our coefficients for the predictors, as well as random effects, or rather intercepts, for cities and states. And in Australia, we actually are able to get 100% when we do have city and state for both test and train data. So it becomes a remarkably easier problem. When we add city, or when we have data that it misses city or state, it goes down to about the same. I think 88.7 as well. The value is featured in the paper. But still, in the United States, we see some success as well with the mixed effects hierarchical model, 88.7. But yes, and compared to the Bayesian paper, right, on Australia from a few years ago, what's different is we basically have soil moisture, and then this is a mixed effects hierarchical model. So whenever we have city and state, we're able to push up to that 100% for our data set. That basically is it. It beats that benchmark, but different data set, but yeah. And one of the reasons we see why, right, in Australia, when we look at those city and state intercepts, those are much bigger than our predictor coefficients. So it's almost like building a different model for each different city, sort of, but it's all handled within training as normal. It's just that our predictors are then customizable for each of our cities and their intercept. So this came out remarkably effective for our test data. For NDVI versus wildfire probability, right? In the United States, I guess what I'd say is our cities, we have a lot, so it doesn't come out quite as beautifully as Australia, where our cities and states, the separation gets us up to 100%, or rather perfect classification. But then we do a little bit of model checking. just to see all three in action, some classic Bayesian theory. But yeah, we see, right, whenever we have like a beta distribution and then we add in what is it? The data, right, to create a prior or to create a posterior. The highest likelihood of a one parameter model, right, is like a 0.5. Yeah, we see the prior a bit less so. It's more spread throughout because we don't have any of our data yet. And then when we look at our models, for the most part, when we do need that one parameter model, right, we see the posterior predictive density. We see all of the non-wildfires are bunched up with probabilities closer to 0. And then all of our wildfires have probabilities closer to 1. So we definitely get a lot of learning out of doing our training and creating these posterior predictive densities, more so than just relying on the properties, right, of a conjugate and adding our data to create a one parameter model. Yeah, so we take our Bayesian models, these three, and okay, yeah, these are statistics for when we don't have city and state data. 88.25 in Australia, 84.07 in the United States. And in general, we sort of show that these Bayesian models are just as effective as any deep learning models today, even as we're working with like pixels in CNNs, convolutional neural networks, etc., and other deep neural networks. So yeah, our Bayesian models are at like 88, 86, 100. We compare to a bunch of different other top line neural network architectures that we take and replicate from some other papers, right? 4-layer, yeah, 20% dropout, ROU. We borrow those architectures. And these guys end up beating the classical machine learning methods, but they don't quite beat our Bayesian models that we present in this paper. So overall, pretty successful experiment. But all of these benchmarks are listed in the paper, comparing the Bayesian regression models to some of the more classical machine learning models. And that would be all.
Excellent.
So thank you very much, Steven. We now have time for questions.
No.
Okay, so can you just go back to the beginning of your presentation? I must admit I was struggling a bit to understand what you meant by classification.
I know it's a very basic question, but just to understand all the rest of it. So, what do you mean by classification in this particular case?
The machine learning problem in general, the binary problem of classifying an instance, like a point in time or space as a wildfire or not a wildfire.
To detect the fire.
Yeah.
To detect propagation.
Just detect a fire.
The existence of a fire.
Yeah.
Okay. So in the end, it's all about satellite images. The best way to do it.
So we take metrics from satellite images, but we don't put the raw satellite image in. We use metrics based off of that. So yeah, it's very easy to compare to like dropping a bunch of features into a decision tree. Yeah.
So what you're trying to assess then is when you have these data, these parameters, to understand which ones actually allow you to more efficiently detect that there is a fire happening, right? Is that the case?
Yeah, more efficiently predict when a wildfire is happening.
Okay, very well. So any other questions? Yes.
Just curious on the data reprocessing piece of your, because we know that these type of models are very sensitive to outliers and so on and so forth. So how did you handle type of situation?
Sorry, could you repeat the
The
question?
outliers and data preprocessing
Yeah.
peaks of global. So just curious on how did you, handle these type of situations with data preprocessing? Because like a lot of features, a lot of inputs you have. So
Yeah. So I was able to get data for most of them. I didn't necessarily really have to worry about missing data for a lot. Most of the APIs are stable. The biggest issue would be geocoding. So that's why I have some different metrics. But overall, right, I think like 293 were successful geocoding in Australia. And then in the United States, most of them weren't. But we have a couple different models, right, where we don't need the city and state, where we just have geolocation. So we use like the spatial kernel. So it doesn't matter that we have missing data, whereas the mixed effects hierarchical model, right, that completely relies on the city and state. It's our only way of having spatial awareness. So bigger issue for that model. Yeah.
and not talking about only using data, but outliers in general, just a sanity check on the data, because a lot of our work as a data scientist sometimes is to check data in the to data reprocessing and everything, but yeah, honestly, very nice.
Okay, thank you, Steven. Now we're moving to our last presentation.
So going back again to, is it the last? To the ideas. So this time with zero-shot LLM, sentiment meets market microstructure, parsimonious feature selections for high-frequency Bitcoin forecasting. Okay, Diego.
Hello again, me again, Diego Dias from Federal University of Espírito Santo. And now I'm going to present a paper led by Moraes, an undergraduate student from UFSJ, and advised by Professor Leonardo Rocha. And as was presented, it's a zero-shot approach for parsimonial feature selection for Bitcoin market. Just a little brief about our motivation. Forecasting Bitcoin at high frequency is very hard problem. So the market shifts regime often and is full of microstructure noise, and volatility can spike with little warning. So part of the answer maybe can be outside the price surge. So mood attention on Twitter, X now, tend to move before the prices do. And LLMs, large language models, let us read that sentiment without handling millions of tweets. That is the zero-shot approach. We use LLM to analyze some tweeters without doing any kind of fine-tuning or retraining, just doing the tasks. The catch here is that once we pile technical indicators, macro data, and social features together, they start to overlap. So when we try to increase the features, what you can see here that we have multicollinearity and overfitting built in. So we did a question here. That's how can we bring LLM social signals into the model harmoniously, keeping the use of information without the redundancy, and still come out ahead once transaction costs are paid. So we try to figure out if to use a lot of features or less features, what's better? More features, more data, more information, or less information is going to be better. So about the background research gap. For serious as volatile as crypto, recurrent networks like LSTM and GRU tend to cope with the complexity better than classical statistical models. So we use two stacked models, both of them, LSTM and GRU, for our experiments. On the sentiment side, the field has great gradually moving from simple word lists like later to context-aware like Sinbird, and more recently using zero-shot ends, the approach that we used here. There's a recurring pitfall in this literature through, though many studies optimize the statistical error such MSE, only getting the metrics, but we need to analyze here also the transaction costs. So we use that on our paper, not only the error, but also the transaction cost. The risk of backtest overfitting. So try enough strategies, and one of them will look great, but luck alone. So tools like deflated Sharp rate, Sharp something related to the Bitcoin market. It's precise to resolve this kind of lucky. So you run a lot of experiments, but to try to get out from the luck. Our take is to question the usual assumption that more data is always better. Instead, we test whether carefully curating the features, being parsimonious, is what actually drives robust economy performance. So I will show you then when you use less features, is much better for this purpose. So we propose a cost-aware multimodal pipeline for forecasting short horizon Bitcoin trends. It brings together three kinds of information: the market microstructure for OHLCV. It's open, high, low, closure, and volume of the Bitcoin market. We add also some technical and macroeconomic indicators. So Nasdaq, gold, a lot of information about that, about the market. And the zero-shot Twitter sentiment analysis using a Llama 2 7B model with no retraining, with no fine-tuning, only a zero-shot. And to keep things lean, we apply recursive feature elimination, RFE, with a random forest, to make feature selection from 30 features down to 17, and using the multicollinearity problem. And then we train the two models, the LSTM and GRU models. And as I said, we use a 0.1% per trade to be more precisely for the market, not only using only the NSE ever, as I said. In our headlines finds that creating the features matters more than how complex the model is. So GRU paired with RFE reaches a Sharp ratio of 5.28. Sharper greater than 2 is very good. Sharper with 5 is very, very good. So it's a nice score for a Bitcoin market. And a 48% return at the 12-hour horizon. So here's the methodology, the pipeline overview. First, the acquisition for Qcoin using the OL HCV about the Bitcoin, Qcoin. The macro proxies, the XI, gold, oil, Nasdaq, more information, more features, and some tech indicators, and 1 million Bitcoin tweets, all the tweets, 1 million tweets regarding the Bitcoins. So after that, we apply the feature selection approach, zero-shot sentiment using Llama 2B, 7B. Then after that, you use RFE plus random forest to come from 30 features to 17 features. And we train and validation the stacked model, LSTM and GRU, using the quick backtest and long short, and 0.1% per trade. Everything was on a fixed 4-hour grid, where each step is still one window. That same frequency drives both the prediction and the trading simulation. And here about the outside of our model. The multimodal data that we applied in our methodology, we use the market and macro, so OHCV in the macros here. And we increased with using the LLM derived features. So we labeled only 10%. So for 1 million, we labeled only 10% of the samples. The labeling was done using Llama 2B chat, quantized to 4-bit, a low precision model, so less memory. So we can use the LLM in our setup. Using a low temperature for reproducibility. So this is always important to mention. Low per temperature, you can run again the experiment when we tend to have the same answer or something next to it. Each tweet yields a sentiment score in -1 to 1, along with intensity of sinus. So the sentiments is -1 is not good, 1 it's okay, it's good, it's a good sentiment. And there are the aggregated per 4 arrow window in segment mean market intensity, emotional intensity, and twitch volume. So after the acquisition, we made the feature selection using RFE and random forest. We start with a diagnostic step, computing with Pearson correlation metrics to get a feel of how much the features overlap each other, the multicollinearity. We made a real selection using RFE. So here, only to see the collinearity, here we used to reduce the features, RFE random forest regressor. And the procedure simply iterates. We fit the forest, we rank the features, we drop the weakest one, then we check and do everything again. Coming from 30 features to 17, so run 13 times this pipeline. We settle on K where that RMCQ flattens out. We can call the elbow, which leaves 17 features out of 30 at the beginning. And this is important to mention, the whole selection uses only training and validation data, so the test sets stay untouched. It's to prevent data leakage, for example. And this gives 4 scenarios to compare. The OHLCV baseline with 5 variables, only data regarding the Bitcoin. We have another scenario that is the Bitcoin's variables plus the macro and technical added, and the last one. So we have the full, the 30, and the last one is finally the environment with only 17 chosen in prediction variables using RFE. Just a little bit about the modules. They are the same architecture. The first layer, we have here the number of units. You use a dropout of 0.2 dropout, 20% of dropouts. Then a second layer is half of the size of the first one. A linear dense layer produces the forecast. And you use an Adam optimizer with a learning rate here. And check with MSC loss, but using the cost per trade. And every setup is run over 10 seeds, and we report the mean using the standard deviation. The equity-based backtest, we use a long short rule files on the predicted return, with a model we showed, which trade pays per 1% transaction cost. So that's very important to really see if the trade is doing great, and cannot use only the MSC. We track 3 different metrics: total return, Sharpe ratio. As I said, more than 2 is a good result for Sharpe ratio, and the maximum drawdown. The point is to see whether the gain survived realistic frictions here, not just whether the euro went down. Just a little about our results using LLM. The twitch volume here is very long tail, so the median 6 at 0. Even the business video reached almost 1,400 of tweets. These are the attention spikes around the market events. Sentiment intensity by context hover close to neutral, also when we average them into course 4 hour beans, if a median point around 0.5. And that part, with that part, we can conclude that it pays to select carefully rather than spam the feature set for its own sake. This median, for example, is a problem. You can see that tweets have no importance in this kind of problem when we use 4 hour beans or something more than that. The correlation structure before training, we take a look at the Pearson correlation heat map only to see the multicollinearity, but we not use that to reduce the features. But we can see here at the figure, this is a problem here because we have a lot of features, variables, prediction variables that have a high collinearity. This is a problem. This is noise. We need to reduce that. So Pearson correlation heat map, the strong correlation among stack and indicator is clear sign of multicollinearity. This is the most important part. While they're linked to the targets stays weak. After see the Pearson heat map, we apply the RFE selection dynamics. So we track the validation RMSE against the number of features kept. A clear plateau appears.
So past that point, adding features bring only marginal gains or noise. So the extra variables contribute noise and redundancy rather than silence. So we fix the operation point at 17 features, 30 from to 17, which strikes a sensible balance between accuracy and parsimony. As for what survives the cut, mostly market microstructure stay at the price and volume variable stay together with momentum and volatility descriptor. The macroeconomic variables play only a supporting role. All the sentiment analysis that we made with LLM and polarity features are dropped. So from the 30 features, almost the entirety that we removed are related to LLM sentiment and polarity. Here we have the reduce the curve and select features. The 17 most important features. The BTC volume for hours is the most important, long return. Then we have the tweet volume here as the last one. So from Twitter, we only keep it this one. And here the elbow said we have just a little noise. So we just stop here and took the 17 features. Here's some results for 12 hours horizon, 3 periods, because each period has 4 hours. And we have the benchmark here, it's just buy and hold, a total return on the sharp. Then compare everything with this benchmark. And we can see that the better results are also using the RFE approach. So when you use the 30 features, you can see a 22, almost 23% of total return. But when you use the same model, but on using instead 30 features, using the 17 features selected, you have a total return of almost 49%. So it can be double more than double. So reducing the features was a good approach here for this proposal. For the longer horizons, best per scenario here, I showed you 12 hours. Now we have the 28 hours to 5 days. So 30 periods. RFE solutions, GIS1 and GIS1, it still remains the strongest option at every horizon, but the absolute numbers fade as the window grows. So from 12 to 5 days or 56 hours, you can see a total return really going down. But it's okay because it's a very long period. It's expected to happen that. But still, GRU plus RFE is a better option. So some discussions. Parsimony is what wins. You can see from the slides. At 12 hours, GRU goes from 48% with RFE down to 22% with the full emitted set. We use the same architecture, same protocol, only the features change. So expanding the inputs naively just adds redundancy and noise, you can see. And the fits becomes stable and the post-cost return weaker. The edge is also short-lived. Stretch the horizon past 2 days and the AI strategy drop below buy and hold. That's a problem because it was our baseline. And as I showed in the microstructure effects get absorbed in the price. The choice of architecture turns out to be secondary. So the most important here is not choose the GRU or LSTM, they're much similar. You need to choose well your features. That was we can keep from the study. And because of RFE discarded the LLM sentiment, whatever short-term edge we see comes from market dynamics and attention volume, not from contextual polarity. So what everyone is texting, posting on Twitter doesn't matter for this kind of problem. As conclusion, we built a parsimonious cost-aware multimodal pipeline that combines zero-shot Llama2B with RFE selection and current predictors. We will test under realistic frictions. The lesson is that curation beats complexity, as I said. So the 17 feature GRU was always the best for all the scenarios with short horizon, of course. There are 2 it's worth stating plainly. First, performance fades over longer horizons since the predictability is sensitive to sudden regime change. Second, the evaluation period was a bull market when everything is going up, going high, and a high of Bitcoins. So the results are conditional on that regime. And the bottom line here is that what drives profitability is partial model selection, awareness of market regime, and cost-aware validation, not big architecture or more features. As feature work, we intend to sharpen the LLM segment extraction. So maybe the contextual polarities adds some sign here, not just noise. Make the modeling regime aware, validation across bull, bear, and sideways market, not only the bull market, but other behaviors, not only the high. And explore adaptive selection with revisitizing which features to keep as horizon and market conditions change. That's it. Thank you very much.
Thank you very much. Now we have time for questions. Yes, please.
It's very good to the presentations. And interesting about the selections. So it's a very wide information regarding to the tweets for the character and also the numeric data using the economic data. So as long as I know that I've heard using for recursive pattern selections was effective with numeric data. Yes. How can you transform from the characters text data into the numeric data?
I don't have details about that because the students did the experiment, but I think it can generate some embeddings and do the work. But I have no details about implementation, sorry. But I can ask the student or can send an email to him and we'll be glad to answer about that.
More questions?
Yeah, one about
some of the context of the work. So this is obviously very interesting because you would think you would become richer if you actually were very good at it. But in the end, there are many other factors that could influence, the predictability of the evolution of the market. So first one, information influences the market, right? So if this information or any other information becomes available,
But the previous one, not the post after that.
I guess you use some training data, right, from the past. I was just wondering, for example, there's two issues. One has to do with the sources that you actually use, whether the tweet is actually a good source or is, just someone less informed people just discussing the topic, right? And the other one has to do with time, right? You selecting the time window that you find better, but or in a sense that is also part of this thing, right? Because you win more if you were able to work with shorter time windows, right? So how do you see these two things being part of future work?
Yes. I really don't see if we can try to figure out what happened along short periods. I think it's that we have now, and I don't see any kind of getting better from this. What I want to try with the students is this. Is trying to sharpen the LLM. Maybe the tweets can bring some more information that we didn't find in this study. Maybe this year is going to improve this prediction. But from now, I want to attack this part.
Okay. Thank you very much. So let me just check
The first one.
if we have the first speaker. Elio, are you there? I don't think he is. Okay, so therefore this means we have reached the end of our session. So thank you everyone for your presence and your presentations, and see you on the next sessions. Bye bye. Okay.